$2 billion apiece. And this vaunted stealth is deathly afraid of the common sun. The Pentagon's greatest scam, sold to us for decades as absolute superweaponry. The most classified bomber turned out to be the most useless piece of expensive plastic in the history of warfare. Our hero today is the Northrop B-2 Spirit. Why is this behemoth hidden in greenhouse conditions like a rare flower? Why was it flown across the ocean without landing for a single mission? And how did American generals brazenly embezzle the state budget right under the nose of the whole world? Right now, together with you, we will strip the top secret stamp from the main pride of the U.S. Air Force. I recommend watching until the end. There will be a moment that will leave many of you speechless. Let's begin. Imagine a map, a huge map. On it is the entire territory of the Soviet Union. And on this map are thousands of dots. Each dot is an anti-aircraft missile system, a radar station, an interceptor at an airfield whose crew is on duty right now. By the end of the 1970s, the Soviet air defense system had become the largest in the world. Not just the largest, it was built as a multi-level shield. Low altitude, medium altitude, high altitude. Everywhere there were missiles, everywhere there were radars, everywhere there were crews ready to push the button. And here's the question: how do you fly through this? The American B-52 Stratofortress strategic bombers, huge, reliable machines, were created for another era. An era where altitude was protection. Climb to 15, 18, 20 kilometers, and no missile could reach you. That is what they thought at the beginning of the 1950s. Then 1960 arrived, and everything changed. May 1st, 1960, Soviet airspace. At an altitude of about 21,000 meters, almost twice as high as normal passenger planes fly today, flies an American Lockheed U-2 spy plane. The pilot is Francis Gary Powers. He is confident. At such an altitude, he cannot be touched. Similar flights over Soviet territory had been carried out for several years. Nothing had ever happened. This time, something did. The Soviet SA-75 Dvina anti-aircraft missile system fired a missile. The missile reached the plane. The Lockheed U-2 was struck over Sverdlovsk. Today this city is called Ekaterinburg. Powers survived. He was captured. Later, he was exchanged for a Soviet spy. But the main thing in this story was not the fate of one pilot. The main thing was that it became clear to everyone immediately. Altitude no longer protects. If a missile could reach a plane at 21,000 meters, then a high-altitude bomber was just as vulnerable as any other. The Pentagon learned this lesson, and they started thinking. They thought for almost 20 years. They tried going lower, flying at ground level, under the radar. The Boeing B-52 was not physically suitable for this. It was too big, too heavy. They created a special plane for low-altitude penetration, the Rockwell B-1. But it too had structural strength limits and limited service life. And the Soviet air defense system was growing in the meantime. New missile systems, new radars, new interceptors. By the end of the 1970s, its radar field covered almost the entire territory of the country, from the western border to the Far East. And that is when Washington made a fundamentally different decision. Not to fly lower, not to fly higher, to become invisible. In 1979, the Jimmy Carter administration officially launched a program called the Advanced Technology Bomber. The leading aviation companies in the country were invited to the competition. The task was formulated simply: create a plane that the enemy's air defense system would simply not see. Not bypass, not outsmart. Specifically, not see. In October 1981, the winner of the contest was determined. The development contract went to Northrop Corporation. And here is where the truly interesting story begins. Because Northrop is not just another aircraft manufacturer. This company had its own old idea. An idea that had been considered unviable for several decades. An idea that had lain in the archives for almost 40 years. And now, its time had come. John Knutson Northrop was born in 1895 in Newark, New Jersey. He never received a formal engineering education. Everything he knew about planes, he learned himself. Through books, through drawings, through his own mistakes. And from a very early age, one thought haunted him. A conventional plane is a compromise. It has wings, they create lift. It has a fuselage, a long tube in the middle where the crew sits and cargo is placed. It has a tail. It keeps the plane in the correct position. But the fuselage and tail are not just useful parts. They are also excess weight, excess drag, extra parts that can break. What if, Northrop thought, you remove everything unnecessary? What if you make a plane that is entirely a wing? No fuselage, no tail, just one large load-bearing surface, inside which everything necessary is contained. This idea is called the flying wing configuration, and Northrop dedicated most of his life to it. In the 1940s, while World War II was already underway, his company received an order to develop an ultra-long-range bomber. It was intended that it should fly from the United States to Europe and back without landing or refueling. The distance, about 16,000 kilometers. Northrop proposed exactly the flying wing, and he built it. The plane received the designation Northrop B-35. Then a jet version appeared, the Northrop B-49. By the standards of the 1940s, it was a machine from another planet. A huge wing with a span of 52 meters, almost like a modern Airbus A380. No tail, no conventional fuselage, just a wing, smooth, continuous, flying. In 1947, the B-49 performed its first flight. The pilot said, "The machine flies surprisingly smoothly. Aerodynamically, it was almost ideal." Almost. Because the flying wing has a fundamental problem. A normal plane is stable on its own. If you deflect it slightly, it strives to return to its original position. The tail acts like a weather vane, like a stabilizer. The flying wing has no tail. It constantly strives to deviate, to yaw, to tip to the side. The pilot must continuously, every second, manually correct the machine's position. On a long route, for hours, it was physically exhausting and dangerous. In 1948, during a test flight, the B-49 crashed. 2 crew members died. In 1949, the United States Air Force shut down the program. All the built machines were cut into scrap metal. Northrop was devastated by this decision. Not figuratively. He personally went to the factory and watched as his planes were being cut. According to some accounts, he wept. Many years later, when journalists asked him about this decision, he said he never fully understood it. That his machines were destroyed not because they didn't fly, but because they flew too well. And someone didn't like that. Whether this is true is hard to say, but the fact remains, the idea was buried. 30 years passed. During these 30 years, a quiet revolution took place in aviation. Not in engines, not in materials, in electronics. The onboard computers of the 1980s could do what was physically impossible for a human. Perform thousands of small corrections per second, constantly, without fatigue, without errors. This, and only this, made the flying wing controllable. The computer takes over what the pilot could not handle. It holds the unstable machine in the required position faster than a person can realize the deviation. And that is when the Northrop engineers remembered the old drawings. But there was one more reason why the flying wing was suitable for the invisible bomber program. A reason Jack Northrop in the 1940s didn't even think about. Form. When a radio wave from a radar reaches a conventional plane, it reflects in all directions, including directly back to the radar. Fuselage, tail, right angles at the junctions of surfaces. Each of them is a mirror for a radio wave. The flying wing has almost no right angles. All surfaces transition smoothly into one another. The radio wave hits the wing and goes to the side. Not back to the radar, but anywhere else, just not where it came from. This is not a coating. This is not a special material. It is just geometry. The right shape, and you are already half invisible. That is precisely why, in 1981, Northrop won the contract. Not only because they knew how to build flying wings, but because the flying wing is the only plane shape that, by itself, poorly reflects radio waves. John Northrop was alive at the time. He was in his 86th year. He was terminally ill. In 1980, a few months before his death, he was brought to a secret briefing. They showed him a drawing of the future plane, a flying wing. His flying wing. Only larger, only invisible. According to eyewitnesses, he looked at the drawing for a long time. Then he said, "Now I know why God has kept me alive so long." He passed away in February 1981. 8 years remained until the first flight of the B-2. Let's deal with one term, once and for all. Radar cross-section. This is exactly what they measure when they talk about the detectability of an aircraft on radar. Imagine, a radar sends a radio wave into the sky. The wave flies, reaches the plane, and reflects back. The radar receives the reflected signal and sees the target. So, the radar cross-section is not the real size of the plane. It is what it seems to be to the radar. How strong a signal returned back. A large plane with flat sides returns a lot of signal. The radar sees it well. A small or specially curved plane returns little signal. The radar sees it poorly, or does not see it at all. Now, the numbers. The Su-27 fighter, one of the best Soviet and Russian combat aircraft, has a radar cross-section of about 3 to 4 square meters. That is about the surface of a regular front door. The radar sees it confidently. The radar cross-section of the B-2 Spirit, from 1,000th to 1/10th of a square meter. 1/10th. That is about the size of your palm. 1,000th. That is less than most birds. The difference is 1,000-fold. How is this achieved? Through 2 ways, and both are important. First, shape. We already talked about it. The flying wing configuration means no right angles, no flat surfaces looking directly at the radar. All surfaces are tilted so that the radio wave goes to the side, away. The engines are hidden inside, above the wing. From below, they are invisible. The air intakes behind special grills that disperse the signal. Even the panel joints on the hull are made at special angles. Every detail on the outside is part of a single geometric calculation. The second way, coating. Outside, the entire plane is covered with a special composition. This composition contains materials, in particular iron-based compounds, that do not reflect radio waves but absorb them. The wave enters the coating and turns into heat. It does not return to the radar, it just disappears. Together, shape plus coating, they give that exact result. A huge plane with a wingspan of 52 meters becomes smaller than a bird on radar. It sounds like the absolute solution, perfect invisibility. But this coating has a problem, or rather, several problems. And they began as soon as the plane left the laboratory into the real world. The coating is very sensitive. Ultraviolet radiation from the sun destroys it. Moisture destroys it. Sharp temperature changes destroy it. Simply put, the plane cannot just be parked at an airfield under the open sky, like they do with all other planes in the world. The B-2 needs a hangar, a special hangar, with a maintained temperature. With humidity control, something between an aircraft shelter and a clean room laboratory. And here, the first truly uncomfortable question. If the plane needs special storage conditions, it means such conditions do not exist at most of the world's airbases. It means the plane is tied to a few specific points on the map. But that is not all. Remember we said that the engines are hidden in the upper part of the wing? This solves the problem of radar detection from below. But engines have something else besides radar reflection. They have an exhaust. A red-hot stream of gases with a temperature of several hundred degrees. Engineers anticipated this. The engine nozzles have a flat shape. There is a system for mixing the hot exhaust with cold air. All this reduces the thermal trace. But completely hiding a temperature of several hundred degrees is impossible. Physics does not allow it. In the infrared spectrum, that is, when observed through a thermal imager, the B-2 is visible. Not as well as a conventional plane, but visible. An invisible plane that is visible in the thermal range. A plane with a coating that is afraid of rain. A machine that needs a special room for storage. These are not the shortcomings of a bad plane. This is the price of absolute perfection in one direction. When you push one characteristic to the limit, something else necessarily becomes vulnerable. And the more expensive the system, the more expensive its vulnerabilities. So, the plane is built, the coating is applied, the tests were passed. Now it needs to be put somewhere. This sounds like a simple task. For any other plane in the world, it is simple. Land, taxi to the parking spot, technicians inspect, done. With the B-2, that will not work. The special radar-absorbent coating, the very multi-layer mixture that turns a huge plane into a dot on the radar, reacts to the environment like a living organism. Ultraviolet solar radiation destroys it. Rain destroys it. The humid air of the seashore destroys it. Sharp temperature shifts, say from a hot day to a cold night, also destroy it. Imagine a very expensive painting, painted with paints that fade in the light, that soften in water, and that crack in the frost. That is roughly how the B-2 coating behaves in the real world. This means the plane needs a hangar. Not just a hangar, a special shelter with a climate control system, maintained temperature, controlled humidity, special finishing materials for internal surfaces, which themselves do not release substances harmful to the plane's coating. The cost of building one such hangar is hundreds of millions of dollars. And yet, you don't just need one. At the time of the B-2's entry into service in 1997, the main base was Whiteman Air Force Base in Missouri. It was there that specialized shelters were built. It is there that the planes return after every combat sortie. This is the first problem. Let's call it the home problem. A plane without its special home is just a very expensive and defenseless machine on an open parking lot. Now the second problem. We talked about the engines being hidden in the upper part of the wing, flat-shaped nozzles, cooling system for exhaust gases. All this reduces the thermal trace. But reduces does not mean eliminates. 4 General Electric F118-GE-100 turbofan engines with a total thrust of 30,800 kilograms force is a huge amount of thermal energy. You cannot cheat physics. Modern aviation thermal imaging detection systems are capable of recording temperature differences in fractions of a degree. In the infrared range, the B-2 is visible. Perhaps not as clearly as a conventional plane, but enough to guide a missile. An invisible plane that is visible in the thermal range is no longer quite invisible. It is a plane with a very specific window of vulnerability. Now the third problem, the most fundamental one. Remember we talked about the instability of the flying wing? About the fact that without constant automatic corrections, the plane simply cannot fly straight? For the B-2, this dependence on electronics is absolute. The flight control system works continuously, thousands of calculations per second, constant correction of position in space. The pilot controls the plane through a computer, not directly. If the system fails, the machine will lose controllability faster than the crew can react. And here's the most uncomfortable question of all. If the plane can only be in a special hangar, it means this hangar is a strategic target no less important than the plane itself. Strike the hangar. The plane will end up under the open sky. The sun, rain, humid air will do their work. The coating will begin to collapse. A $2 billion machine gradually loses its main quality, invisibility. This is not a hypothetical scenario. This is the logical consequence of the plane's very concept. The more perfect the system, the more precise the conditions for its operation must be, and the more vulnerable it becomes when these conditions are violated. The creators of the B-2 understood this. They tried to compensate for it. But some things cannot be compensated for. You can only accept them as the price for outstanding capabilities. The question is this price worth what you get in return? The B-2 has nothing on the outside. This is fundamentally important. There are no external pods under the wings, no launchers on pylons, no anything at all that sticks out, because any protruding element is a reflector for a radio wave. One suspended pod on the outside, and half the work on reducing detectability goes down the drain. Therefore, everything, absolutely everything, is hidden inside. In two large compartments in the lower part of the hull. They are closed flush with the wing surface. They open only at the moment of application, and immediately close back. Let's look at what exactly fits in there. The first option is nuclear. The B-2 can carry up to 16 free-fall nuclear bombs. Two types, B-61-11 or B-83. Freefall means exactly what you think. The bomb separates from the plane and falls down under the force of gravity. No engine of its own, no guidance in flight, only physics and a pre-calculated drop point. 16 such bombs on one plane. This is a colossal destructive potential, concentrated in a machine with a crew of 2 people. The second option, conventional unguided aerial bombs. 80 Mark 82 bombs, each weighing 227 kilograms, or 16 Mark 84 bombs, each weighing 907 kilograms. That is almost a ton for each. Or 36 CBU-87 and CBU-89 cluster bombs with the telling name Gator, that is, alligator. 80 bombs. 1 plane. 2 pilots. For comparison, in World War II, an entire squadron of 12 Boeing B-17 bombers carried about the same. The third option, high-precision guided bombs. Here the key word is guided. Unlike free-fall bombs, they can correct their flight after the drop. JDAM series bombs. Joint Direct Attack Munition. These are ordinary bombs to which a special tail unit with a satellite navigation receiver is installed. After the drop, the bomb guides itself to the target by coordinates. The deviation from the target, on average about 10 meters. The B-2 can carry up to 80 such bombs of 227 kilogram caliber, or 8 guided GBU-27 bombs, Paveway 3 laser-guided bomb, with laser guidance. The fourth option, cruise missiles, up to 16 AGM-158 JASSM cruise missiles, Joint Air-to-Surface Standoff Missile. A cruise missile is already something fundamentally different. This is not just a falling bomb. It has its own engine, its own guidance system. After launch, it flies independently, bypasses the terrain, chooses the route, finds the target. Launch range, 370 kilometers. This means the plane, theoretically, can launch a missile without entering the engagement zone of many anti-aircraft systems. Theoretically. Because here arises one number that cannot be ignored. The detection radius of a modern Russian S-400 Triumph anti-aircraft missile system is about 600 kilometers. 370 versus 600. To launch a missile from maximum range, the plane must already be inside the detection zone. This does not make cruise missiles useless. The B-2's radar detectability is indeed small. Perhaps it will not be detected, but this is no longer a guarantee. It is a probability. And a strategic bomber whose safety is based on probability is a completely different conversation. So, inside the B-2 is everything necessary. Nuclear option, conventional bombs, precision munitions, cruise missiles, full set. But here's the question we haven't asked yet. How much does it all cost? And how did it happen that one plane cost more than some countries spend on their entire army for a year? There is such a principle in economics. It is called the scale effect. The meaning is simple. The more units of goods you produce, the cheaper each individual unit becomes. The costs for development, for building factories, for training personnel, for creating tools. They are the same regardless of whether you make 10 planes or 132. But if you divide these costs by 132 planes, each has a small share. If you divide by 21, each has a very large share. That is exactly what happened with the B-2 program. Let's go back to the beginning, to 1981, when the contract was just signed and everything was still ahead. The United States Air Force planned to purchase 132 planes. 132 is a full-fledged strategic fleet, enough to replace a significant part of the aging bombers and create a truly new generation of aviation. With such a quantity, the cost of one machine was estimated at about $500 million. Huge money for one plane, even by the standards of the 1980s. But in the context of strategic armaments, explainable. Then 1991 came. The Soviet Union ceased to exist. The Cold War, which had lasted 46 years, which had given birth to the very idea of an invisible bomber, was over. The United States Congress asked a logical question. If the main threat no longer exists, why do we need 132 stealth bombers? An answer that would satisfy the congressman was not found. The order began to be reduced, first to 75 planes, then to 50, then to 20. In the end, they stopped at 21. 21 planes instead of 132. And the development costs didn't go anywhere. They had already been spent. Fully. According to various estimates, about $23 billion was spent just on the program's development. This is 1990s money. If you recalculate it to today, taking inflation into account, the sum would be significantly larger. 23 billion divided by 21 planes. Just the development costs, already more than 1 billion for each. Add the production cost of each machine. Add special hangars, special equipment, specially trained personnel. The final cost of one B-2 Spirit, taking into account all program costs, was about $2.1 billion. $2,100 million. For one plane. With a crew of 2 people. Let's try to imagine what this means. A nuclear-powered aircraft carrier of the United States Navy of the Nimitz class, the largest combat ships in the world, cost about $4.5 billion each. This is a ship 330 meters long, with an air group of 70 to 80 planes, with a crew of about 6,000 people. 2 B-2s cost about the same. Or here is another example. The McDonnell Douglas F-16 Fighting Falcon fighter, the standard multi-role fighter that is in service in 25 countries of the world, costs about $35 million. For the cost of one B-2, you can buy 60 F-16 fighters. 60 planes versus one. But that is not all. After the plane is built and accepted for service, the expenses do not end. They continue every day. B-2 operation costs about $135,000 per hour of flight time. This is not a typo. $135,000 an hour. For comparison, an hour of flight of the Boeing B-52 Stratofortress strategic bomber costs about $70,000. The B-52 was developed in 1952, 70 years ago. It is still in service, and it costs half as much to operate. Here is where the very question arises that the Pentagon preferred not to ask out loud. If for 21 machines, they paid as much as would have been enough to re-equip entire branches of the armed forces, what exactly was bought for this money? Capabilities, that is understandable. The capabilities are outstanding. But capabilities exist for specific tasks. And tasks, that is a separate conversation. Because the first time the B-2 was used in real conditions was exactly when nobody expected it. And this experience cast doubt on many things. March 24, 1999. The North Atlantic Treaty Organization began a military operation against the Federal Republic of Yugoslavia. The operation was named Allied Force. In the very first nights, planes from air bases across Europe headed for the Yugoslav sky. Fighters, attack aircraft, bombers, and somewhere among them, invisible to radars, flew the B-2s. But here is what is important to understand immediately. They were not flying from a base in Europe, not from an airbase in Germany or Italy, not from an aircraft carrier in the Mediterranean. They were flying from Whiteman Air Force Base, Missouri, United States of America. The distance from Whiteman Air Force Base to the territory of the former Yugoslavia is about 8,800 kilometers in a straight line. The maximum range of the B-2 without refueling is 11,100 kilometers. That is enough for one way. Barely. This means aerial refueling over the Atlantic Ocean, then the flight over Europe, exit to the target, drop munitions, turn back, back across the Atlantic, refuel again, land in Missouri. The entire route took about 30 hours. 2 pilots, 30 hours in the air. Without the possibility to stand up. Get proper sleep. Get out. For this, the crews were specially trained. They practiced sleeping in turns right in the seat. Special nutrition. Special physical exercises right in the cockpit. The question is asked, why? Why couldn't European bases be used? The answer is simple. You already know it. Because there are no suitable hangars. Because the special coating requires special conditions. Because the plane cannot just be parked under the open sky at an Italian airfield and raised into the air again in the morning. 30 hours in one direction is not just a combat sortie. It is a demonstration of how complex the entire logistics of this program are. Now about the results. During Operation Allied Force, from March 24th to June 10th, 1999, B-2 planes performed 49 combat sorties. 49 sorties from Missouri and back. 49 times for 30 hours in the air. About 656 guided munitions were dropped. This is about 11% of all guided bombs used in the operation. From the point of view of hit accuracy, the results were high. The plane did exactly what it was created for. It broke through air defense and precisely hit targets. But here is the question that suggests itself. The air defense of the Federal Republic of Yugoslavia, how strong was it? The honest answer, it was not the threat against which the B-2 was created. Yes, anti-aircraft missile systems were there. Yes, they worked. Yes, they posed a danger. But it was not a multi-level echelon system with modern radars and long-range missiles. It was an obsolete infrastructure, created back in the Soviet era, with limited update capabilities. Simply put, the B-2 was used not against the enemy for whom it was created. It is like using a surgeon's scalpel for slicing bread. It cuts, but a knife would have handled it no worse. And it was in this operation that one episode occurred, which is still cited by everyone who deals with the topic of stealth aircraft. March 27th, 1999. On the third night of the operation, a plane was shot down. Not a B-2, another stealth aircraft, the Lockheed F-117 Nighthawk attack aircraft. It was shot down by a Yugoslav anti-aircraft missile system of Soviet production, Neva, a modernized version of the SA-125 complex, which entered service back in 1961. An almost 40-year-old system. How did an obsolete complex shoot down a stealth plane? The division commander, Lieutenant Colonel Zoltan Dani, applied a non-standard approach. He used a radar at significantly lower frequencies than usual. Stealth planes are designed with specific frequency ranges in mind, those used by modern guidance systems. At low frequencies, their detectability increases sharply. The F-117 pilot, Lieutenant Colonel Dale Zelko, ejected and was rescued by a search and rescue group. But the fact remained a fact. A stealth plane was shot down by a 40-year-old anti-aircraft complex with non-standard use of a radar. This did not mean that the stealth technology doesn't work. It works, and works well. But it meant something else. Invisibility is not an absolute. It is an advantage in specific conditions against specific threats. Change the conditions, and the advantage diminishes. This is a lesson that was important to learn, and it is directly related to the question that we will ask in the next part. Let me introduce you to one plane, the Boeing B-52 Stratofortress, a strategic bomber. It first took to the air on April 15, 1952. Think about that date, 1952. This is 4 years after the appearance of the first Soviet nuclear weapon. This is the year when most people watching this video were not yet born, and some of their parents weren't either. This plane is now over 70 years old, and it is still in service with the United States Air Force. Moreover, according to current plans, it will be in service at least until 2050. That is almost 100 years from the moment of its first flight. How is that possible? Why is a plane developed back under President Harry Truman still considered combat capable? Let's figure it out. Because the answer to this question is directly related to the question about the purpose of the B-2's existence. The B-52 is a huge machine. Wingspan, 56.4 meters. That is 4 meters more than the B-2. Length, 49 meters. That is more than twice as long as the B-2. Crew, 5 people. Maximum combat load, about 31,500 kilograms. That is about 4,000 kilograms more than the B-2 even after modernization. There are 8 engines. Pratt & Whitney TF33-P-3 turbofans, each with a thrust of about 8,000 kilograms force. Maximum range without refueling, about 14,150 kilometers. That is 3,000 kilometers more than the B-2. It is not stealthy at all. Its radar cross-section is huge. Any modern radar will see it from hundreds of kilometers away. But here is the thing. The B-52 does not need special hangars. It can sit on an open parking lot in the rain, snow, and sun. It is based at almost any airfield with a sufficient runway length. The cost of 1 hour of its flight is about $70,000. Reminder, for the B-2, it is $135,000, almost twice as cheap. And, most importantly, over 70-plus years of service, the B-52 has undergone numerous modernizations. Today it knows how to use almost the same armament as the B-2. High-precision JDA-M bombs with GPS guidance. It can. A GM-86C air-launched cruise missiles with a nuclear or conventional warhead. It can. The launch range of such missiles is about 2,400 kilometers. That is 6 times the range of the AGM-158 JASSM missiles that the B-2 carries. That is, the B-52 can hit a target without entering the detection zone of most anti-aircraft systems at all. Without stealth. Without special coatings. Without climate-controlled hangars. Without 30-hour flights from Missouri. Just took off. Launched a missile from 2,400 kilometers. Flew back. Against this background, the question sounds increasingly sharp. Why is the B-2 needed? Supporters of the program give one answer. It sounds like this. The B-2 is indispensable, or there is a truly strong, modern air defense system. One that sees cruise missiles at a great distance. One that intercepts them before they reach the target. One whose radar works on different frequencies simultaneously. In such a situation, they say, only a plane with minimal detectability is capable of breaking through. No cruise missile will help, only the B-2. This argument is logical, and it cannot be simply dismissed. But it has a flip side. Exactly such an enemy, possessing the most modern and developed air defense system, simultaneously has the best detection means. Multi-frequency radars, thermal imaging surveillance systems, airborne early warning and control aircraft, reconnaissance satellites. It is precisely against such an enemy that the B-2's stealth works worst of all. Because exactly such an enemy is purposefully looking for ways to detect stealth targets. We already saw how this works in practice. 1999. A 40-year-old anti-aircraft complex. A non-standard radar frequency. A shot-down stealth plane. What will happen when against the B-2 there will work not an obsolete complex with the non-standard approach of one officer, but an entire system specifically designed to detect stealth targets? This is not a rhetorical question. This is a practical question that military planners face every day. And while this question remains open, the question about the real combat value of the most expensive plane in aviation history also remains open. Perhaps it is indispensable. Perhaps this is the best investment possible. Or perhaps the truth is somewhere in between. And it is exactly this somewhere in between that costs $2.1 billion per piece. But the story does not end there. Because while these arguments were going on, in the hangars of Northrop Grumman, they were already building something new, a successor. A plane that was supposed to fix everything the B-2 was reproached for. And when it finally appeared, the first thing everyone who saw it said, "It looks familiar." Before talking about the future, one must speak about one day. February 23, 2008. From Andersen Air Force Base on the island of Guam, a B-2 Spirit plane was taking off. Tail number 89-0125. Proper name, Spirit of Kansas. Proper names for these planes are a tradition. Each machine bears the name of one of the United States. Spirit of Missouri, Spirit of California, Spirit of Texas, Spirit of Georgia. 21 names, 21 planes. On that February morning in 2008, Spirit of Kansas began its run on the runway. Something went wrong in the very first seconds. The air data sensors, instruments that measure speed, air pressure, and angle of attack, gave incorrect readings. The reason turned out to be trivial and simultaneously indicative. At night at Andersen Air Force Base, it rained. Moisture got into 3 of the 34 air data sensors. The sensors distorted the readings. The onboard computer received incorrect information and made an incorrect decision about correcting the plane's position. Remember, we said that the B-2 physically cannot fly without constant computer correction, that the pilot controls the machine through a computer, not directly? That is exactly what happened. The computer, having received false data, began to correct the plane's position in the direction opposite to what was needed. The machine sharply raised its nose upward during takeoff. The pilots managed to eject. Both survived. Spirit of Kansas crashed onto the runway and burned. The cost of the lost machine is $1.4 billion. The cause of the accident? Moisture in the sensors. Rain. The very same rain from which the plane is supposed to hide in a special hangar. This time, it got to it right during takeoff. After this crash, 20 planes remained in service. 20, and not a single new one will ever be built. B-2 production was finally halted back in 1999. 20 planes, for the entire remaining service life of the program. They are cherished, carefully maintained, regularly modernized, but every sortie is an irretrievable resource. Every flight accident is a loss that cannot be compensated for by a new plane from the factory. And that is exactly why, back in the early 2000s, the Pentagon began thinking about a successor. In 2006, the start of a development program for a new strategic bomber was announced. The official program designation, Long Range Strike Bomber. In 2015, the development contract was awarded to Northrop Grumman, the very same company that built the B-2. The very same company whose founder dedicated his life to the idea of the flying wing. The new plane received the designation B-21 and the proper name Raider, in honor of the famous raid of Lieutenant Colonel James Doolittle on Tokyo in April 1942. The first public unveiling took place on December 2, 2022. When the tarp fell and the plane appeared before the cameras, the first reaction of most observers was the same. It looks like the B-2. And it's true, the B-21 is also made in the flying wing configuration. The same characteristic silhouette. The same serrated edges of the wing dispersing radio waves. The same lack of tail fin. Jack Northrop's idea, the very same one that was buried in 1949, is again embodied in metal, for the third time. But for all the external similarity, this is a fundamentally different plane. The first difference? Size. The B-21 is smaller than the B-2. Exact dimensions are officially classified, but according to open estimates, the wingspan is about 40 meters against 52 for the B-2. Smaller size, less detectability. Smaller requirements for hangars. The second difference, stealth technologies. Over the 30-plus years that have passed since the B-2's development, materials and coatings have stepped forward. New radar-absorbent materials are more resistant to the environment. They do not require such rigid storage conditions. This does not mean that the B-21 can be left in the rain for a week, but the infrastructure requirements are significantly softer. The third difference: electronics and capabilities. The B-21 was designed with operation as part of a single combat network in mind. It can exchange data with other planes, with satellites, with ground command posts in real time. It is also designed for the use of advanced hypersonic munitions, which are only just being developed. The B-21 Raider performed its first flight on November 10, 2023, from Edwards Air Force Base in California. And here is that very fundamental difference, which changes the entire economics of the program. The United States Air Force plans to purchase at least 100 B-21 planes, perhaps more. 100 versus 21. Remember the scale effect? The very principle that turned the B-2 from a $500 million plane into a $2 billion one? Now it works in the opposite direction. The cost of one B-21 is estimated at about $700 million. This is 3 times cheaper than the B-2, but only because they ordered 5 times more. If they had ordered 21 again, the numbers would have been completely different. This is not just a detail. This is a lesson that the Pentagon has finally learned. The cost of a program is not determined at the drafting table. It is determined in the office where the quantity is signed. Now a fleet of 20 B-2s continues to serve. According to various estimates, they will be operated at least until 2032 to 2035, until the moment when the B-21 fleet gathers enough machines to fully take over the predecessor's tasks. 20 planes, each with the name of a state, each with a multi-billion-dollar history behind it, each a living embodiment of the idea of a man who passed away 8 years before his dream first took to the sky. They fly. As long as they fly. And as long as they fly, the question of whether it was worth the money spent hangs in the air, just as their characteristic triangular silhouette hangs in the sky. The answer to this question is in the final part. So, we have covered the whole path, from a map with thousands of dots, anti-aircraft complexes across the vastness of the Soviet Union, to the triangular silhouette over Whiteman Air Force Base, from Jack Northrop, who wept watching his planes being cut, to his idea, embodied in the most expensive flying machine in human history. Now it is time to sum up. But first, a few numbers. For the last time, I promise. B-2 program, final score. Development costs, about $23 billion. Production cost of 21 planes, about $21 billion. Operating costs over all years of service, according to various estimates, another several dozen $billion. The total sum that the B-2 program cost American taxpayers over the entire time of its existence, according to various calculations, from $44 to $50 billion. This is not just big money. This is money that is hard to even imagine as a concrete image. Let's try. With this money, one could have fully financed the construction of the International Space Station about 4 times. The cost of the entire International Space Station program is about $150 billion, and 15 countries participated in it. With this money, one could have built about 50 modern military hospitals, or fully re-equipped several air wings with next-generation fighters. But the money is spent. The planes are built. The history is written. Now, an honest breakdown. What did the B-2 give to aviation and military affairs? First, and this is undeniable, it proved that the concept of a heavy stealth strategic bomber is realizable. Not in theory, in practice. Before the B-2, stealth existed in relatively light machines. The Lockheed F-117 Nighthawk, accepted for service in 1983, was not a bomber in the full sense of the word. It was a subsonic attack aircraft with limited combat load. The B-2 showed stealth and strategic power can exist in one machine. A huge plane with a combat load of more than 22,000 kilograms can be practically invisible to radars. This was a technological breakthrough, a real one. Second, It provided invaluable practical experience. Materials, coatings, control systems, aerodynamic solutions, worked out on the B-2, all this formed the basis for the next generation. The B-21 Raider was created by people who lived for 30 years with the problems of the B-2, who knew every one of its vulnerabilities from the inside. This knowledge cannot be obtained in a laboratory. Third, it changed the very thinking about strategic aviation. After the B-2, the concept of stealth became a mandatory requirement for any prospective combat aircraft. Not an additional option, a mandatory requirement. Today, no major aviation power designs new combat aircraft without taking into account the principles of reducing radar detectability. This is the B-2's legacy, and it is real. But now, the other side of the account. What did the B-2 not give? It did not change the balance of strategic forces as originally planned. 132 planes could have created a fundamentally new architecture of strategic aviation. 21 planes is an elite, expensive tool for very specific tasks. It did not solve the problem of infrared detectability. Over 30+ years of operation, this vulnerability remained a vulnerability. Modern thermal imaging detection systems are becoming ever more sensitive. It did not prove its indispensability in real conflicts. Yugoslavia, Afghanistan, Iraq. In none of these cases was there an enemy against whom the B-2 would have been truly the only possible solution. There was always a cheaper alternative. And it opened a question that is still not closed. The question sounds like this. Does there even exist a scenario in which the cost of $2.1 billion per plane is justified from the point of view of combat effectiveness? Those who say yes cite one argument. Only the B-2 is capable of breaking through a modern echeloned air defense system and hitting targets that are otherwise unreachable. Neither a cruise missile nor a conventional bomber will pass through such defense. Only it. This is a strong argument, and it is honest. Those who say no cite another argument. Exactly such an enemy, with the most powerful air defense system, purposefully develops means for detecting stealth targets. It knows about the existence of the B-2. It knows about its vulnerabilities, and it is preparing. This is also an honest argument. The truth, most likely, is located where it usually is in such disputes, somewhere in the middle. The B-2 is not a useless waste of money, and not an absolute means of achieving a goal. It is the most expensive compromise in the history of aviation. A machine that achieved the impossible in one direction and paid for it with vulnerabilities in another. A plane whose existence was determined not only by engineering solutions, but also by political, economic, and historical accidents. If the Soviet Union had not ceased to exist in 1991, if the order had remained 132 planes, we would be talking about it quite differently today. But history does not know the subjunctive mood. There are 20 planes with the names of states. There are 30 hours over the Atlantic there and back. There are special hangars with climate control. There is moisture in the sensors, and $1.4 billion burned on the runway of the island of Guam. And there is a question I want to leave to you. Not about the B-2, about a principle. When we create something so complex, so expensive, so dependent on ideal conditions, at what moment do we cross the line? The line between an outstanding achievement and a system that has become a hostage to its own perfection. The B-2 found this line. Or, more precisely, it drew it. Because following it came the B-21. Cheaper, more practical, 5 times more machines. The same idea of Jack Northrop, the same flying wing configuration, but with lessons that cost $50 billion. Maybe that is the true value of the B-2, not in what it did, but in what it taught. Sometimes, the most expensive lesson is the only one that is truly remembered.